So we're doing another session on this group theory question, and I'm happy that I saved the next step in here because I would have actually forgotten about it. So the next step that we wrote to ourselves as a note was to study the actions from C3 to D. So essentially, we were working in the last session on understanding that, and I kind of have to admit that I had a bit of sort of the kind of like special moment where you realize that you kind of truly have understood something. But anyway, let's try to capture more of these moments. So, um, again, the whole point of these problems is that we're having the action S. Sorry, we're having a group S, we're having a group D, and then a group G that is constructed as S, as a D times S with an impartial D impartial. I don't know what's that called, but like it's an was it an not like a direct product, but like a partial product or something like this. I think R times. It's called R times. What was that? Partial product. Partial product. What was that product called? Partial product. So, and what we want to do is now focus on the action thing, right? Because it's essentially what we have to do is like this dr times s. Where are the action of it? So we need to deep dive into action. We know what we did is we know a way to code. It's gonna open or not? This is this one. This doesn't open. I think maybe because Grok is thinking. It's just my internet that bad, I guess, or what's going on here? Why it doesn't know? Why don't the other chats open? I don't know. I'll get back to it. But we had code. We had code that was actually building these with SymPy, and then adding different rules, and then calculating isomorphism between these and these, which kind of makes sense. Maybe there's something to say about doing a quotient group like S over something. It potentially is isomorphic to that something if you do that enough times. As in, like, you reduce the order at least, right? Not that matter. Yeah, well, yeah, the order matters because it's the number of elements, but yeah, it's fine. Now we're trying to understand what the action. I want to explore actions in SymPy because I mean, this seems to. This kind of helps me. Somehow I notice this helps me understand a bit more because I can see how it's done in code. Well, that is reconnecting. I'm gonna try to reload this page. Grok is currently under. Yay, great. Okay, so we're not gonna be able to work on this right now, or what? As quickly as possible. Maybe we'll just do fast, or it's just that Grok is. It's not even loading. Anyway, we'll use old plain either Perplexity or Google in the meantime, while our intelligence is coming back. Although maybe I'm thinking maybe the voice assistant is working well today. Let's see. No, it also doesn't look like it's working well. All right. We'll come back to it in a second. Anyway, we're trying to understand. So let's just what do we do? Let's just do how do you define actions from one group to another group theory using SymPy? See if Perplexity is able to help us there a little bit. In SymPy, defining actions from group to another, group actions generally approached through permutation groups. Whoa! Okay. SymPy's combinatorics module provides tools to work with permutation groups which can represent group actions on sets by permuting elements. Okay. Define the groups. You can create groups using permutation group generations and represent the action. A group action can be viewed as a homomorphism from one group to the group of permutations on a set. In practice, it means having a first group act on a set via permutations defined on the second group. Use permutations as group elements. The elements of the group acting are permutations that specify how elements of the set are mapped. Example, snippet, define a permutation group. For more complex and specific group actions involving homomorphisms between groups, to permutation elements in the second group which acts on the set. High-level labeled for defining group actions as abstract morphisms, but using permutation groups, you effectively represent group actions on sets. Permutation groups. So what are permutation groups? What are permutation groups? No, don't want an image. A permutation group in mathematics is a group whose elements are permutations of a given set, and whose elements are permutations of a given set, and its group operations is the composition of these permutations. More precisely, consider a non-empty set X, the set of all bijections 1 to 1 and onto functions from X to itself from a group and the function composition known as the symmetric group on X. The permutation group is any subgroup of the symmetric group. Examples. The symmetric group Sn is the group of all permutations of an n-element set. The alternating group An is a subgroup of Sn because it is isomorphic to some permutation group. Making them a concrete representation of abstract groups, they also capture the concept of group actions. Describe how group elements can permute elements of a set. Let's go back to group actions. Can you give me a formal definition of a group action? While Grok is back online. That is a shame. Hello? No. A formal definition of a group action is as follows. Given the group G and a set X, a group action of G on X is a function Gx that maps X. So satisfying the following two axioms for all GH belonging to G and X belonging to X. The identity, so the element of EG acts as the identity function on X. The action respects the group operation meaning. In other words, applying the group element Gx to X is the same as applying H to X, then applying G to the result. Okay, but I mean action, so, but then I don't understand one thing. So the only possible non-trivial action of S on D. So, and what is an action from 1 group to another group. As a group homomorphism. Okay, so an action is really kind of a function. So if you say an action is how you define, because I guess the action from a group on a set is just a way to define. It's probably just a way to kind of project that group into a set, right? It's say like the group is the abstract definition of how the elements behave and under one operation, and that action is just a way to apply this to a set, while an action from one group to another group is typically a homomorphism. So given two groups G and H, a group homomorphism is a function that goes from G to H. Okay, so you give G as an input and it gives you H as an output. That preserves the group operation. This means for all elements of G, the function of G1 times G2, this being the operation, is the same as that function times that function. Okay, where the operation of the left group is such a homomorphism respects the identity elements as well. So it's just a mapping, isn't it? Isn't just a way to map? Yeah, acts by mapping elements of G into elements of H in a way that it's consistent with the group structures. Okay, well that is easy. Is that the definition of a homomorphism? What's the technical homomorphism? Because then, oh, Grok boy, we're not going to use. Oh, wait. Grok's back? Is Grok back? Yes, Grok's back. Looks like Grok is coming back. That's good. Then what is a trivial action? Then how do you find a trivial action? So a homomorphic, given two groups, a group homomorphism is a function such that for all elements property holds. Yeah, okay, that's all fine. That's all good. Okay, yeah, sure. All right. I think let's see if Grok is back. Understood. Okay. Okay, so what I'm gonna do is, and again, I want to try to play with. I want to play again with the voice assistant. Okay, but it's still not kind of working. Okay, it's all good. Give me some example SymPy code that shows me how to represent a group action on another group. So, and here it says with SymPy you do this with permutation groups. So define permutations in S3, symmetric group on 3 elements. So the identity permutation, what the compute the conjugate. What? F permutation G, what is that? We define 2 permutations in S3, G identity and H, swaps 0 and 1. The conjugation action is computed. Since G is the identity, the result is H, but this shows the mechanism for conjugation. Okay, but that's the one. So let's take a step back and be more generic, or more concrete actually. So what about we just do like C3 and C2? Like, can you define C3 and C2 and SymPy, and then action. Actually, I think that's not, I mean, the action. So, wait. A step back, step back, step back, step back. Let's take a step back. How is action between two groups, G and H, relevant when calculating GR times H? Partial product? Maybe that's just something that you need to define, essentially. I mean, it's not a property, it's like, it's just part of the R times operation. You need to define an action. You need to define how you're going to map the elements, right? I guess. It's just saying the action, and it's just telling you use the only non-trivial action between these and that. So use the only non-trivial action that you can use to map, you know, to do this operation. It's part of the specification of that operation. I guess that's what we're getting at. That's my guess, okay? Semi-direct product, a specific group construction that involves a group action, and the sentence action is key. Okay. Term partial product, which seems to be a semi-direct product. It's not a standard term. Yeah, exactly. So a group action of G and H is a homomorphism. Okay, we know that. It's just a mapping between one group to another. All fine. Semi-direct product. The semi-direct product G and H, and yeah, this kind of has that action there. This is a way to combine two groups, G and H, using a group action. The underlying set is the Cartesian product, but the group operation is defined using the action. Okay, so you've got the Cartesian product of the two groups, but you define the operation using the action. Okay, I'm not going to read more because that's just too much. Now, looking at C3 and C2. Okay, so what is C2? Okay, what is the C2 group? I guess it's the thing with the cyclic two elements thing. Yeah. What is then C2 squared? I guess it's C2 times C2, right? I guess so. Component-wise, properties. It's isomorphic to these round. No, I guess that's what I meant. Is the direct product. I guess it's these. I guess it's what you could say is these, right? So it's this with four elements. C2 times C2. So it's basically the Cartesian product, and then the operation is just the element-wise operation. So so G1 H1 G2 H2 is G1 G2 and H1 H1. Not so sure that is obvious, but okay, let's just think of it like these. And so you've got four elements, and that's how you multiply them together. This is the Klein-Vorgruppe, vierere Gruppe in German, which is the billion, with every non-empty element having order 2. So you have these elements basically. That's C2, and so C3 and C3. Okay, so now let's think about these. So how do you map? So can you put on a table the structure of C2 squared and C3 side by side, please? We need to kind of then I guess when we're doing this, what we need to understand is we have, so we've got these. So we need d times s. So d is c2 squared, and s is this. Okay. Now we need to think of the action, the only possible non-trivial action. So we need to understand that. But we're not doing C3, we're doing S. We have to remember that we have to come back to this before, when we actually construct G, before we move to the actual question. But first we need to understand the action between C3, the action from C3 onto C2 squared, and like what is a trivial action in that context, right? So you've got these four elements and these three elements, right? So now that's interesting because we would need to do, so we would need to figure out a way. So how would you map these, right? I guess what will be the action? So if we were to do a semi-direct product, how we would map the two groups? How would you map one group to another? How would you map one group to another? So okay, so here you have the table. What is that? Whatever it is. Element orders, abelian, yes, order 3 or 4. On D, right? So it's a mapping from C3 to C2 squared. Do you have to map something to the same element twice? How would you approach a homomorphism or a mapping from C3 to C2 squared? What are you mapping? You're mapping the elements? You're mapping the elements. Yeah, okay. So you're mapping, again, remember, the homomorphism is, it's a map that respects the operations on both sides, right? So the operation in this case, I think what that would mean is that probably B is mapped to both EA and AE. That's what my intuition tells me. Because then B squared equals the identity. No, something like this, right? So we have to respect the operations. The operation is that you have E, B, and B squared such that B squared equals E. And in this case, we have these. And the operation is the component-wise thing. So E times A is EA, and EE times AE is AE. So you have those rules. I just don't know how would you approach that structurally, but let's say how you approach homomorphism of C2 squared. Yeah, so it's from C3 to C2, yeah. Preserves the group operation. So for all x, y, and C3. Since C3 is generated by B, homomorphism is determined where phi B maps and phi B must satisfy the relations of C3. Since C3 is E, we need, okay, so you need okay, so you're basically saying that's kind of the only rule, right? So you need to map you need to make sure that whatever transformation you do is B3 is the same as applying this to B3 times. Which would be these, and I don't know how would you equal that to EE. Well, yes, because the identity of one group must be the identity of the other. I guess that's the point. The order of A must divide by the order of B, which is 3. Order 1. I don't get that. Since 3 doesn't divide 2 or 1, the only element in C2 that phi b can map to with these is EE, the identity. Not so sure how that order and what that means here, really. If it is E, then it's E, which works. Then if E, then exactly, okay, which fails. Similarly, this fails, because it's kind of like a bit of a trial and error, right? But it's like, okay, that kind of makes sense. It's the only consistent choice, leading to the trivial homomorphism. So there is a concept of trivial and non-trivial. Okay, I'll be back.